You're listening to the VSL Aviation Podcast. I'm your host, Seth Lake, and this is episode 21. Thanks for listening. Thanks for watching if you're joining us on YouTube. In today's episode, we're going to continue our discussion on the multi-engine add-on rating, going through the commercial syllabus or the commercial airman certification standards for the multi-engine add-on. So if you're wondering the basics of what it takes to get your multi and the training required and what's going to be covered in your Checkride, you need to go back and listen to episode 20 where we kind of introduce that. And then this episode, we're going to clean up the rest of the ACS and get into some more details of multi-engine flying. So stay tuned. Before we get to that, I just want to say thank you to all the people that have provided feedback either through email or YouTube comments, or reaching out on Patreon especially. I have some new patrons. I need to make sure it's kosher for me to read off everybody's names, but I'll do that probably next episode. I'll start reading off the names of all the Patreon sponsors, but they've decided to financially support the show, which I really appreciate, because if you go out and do that, that just allows me to devote more time to doing these shows, either the podcast or video, and build this content that's going to hopefully help you be a better pilot and have a more successful Checkride, which is what this is all about. On that note, I'm about to launch a Facebook group. So Facebook group that you'll have access to if you join Patreon. This Facebook group is really just going to be all about pilot mentorship. So I'm going to host basically live streams on there, as well as kind of ask me anything type sessions. I'm going to try to do it initially on twice a month, so every 2 weeks. But at least twice a month, we'll have an AMA in there. So if you're having a Checkride come up or you have any questions related to taking your Checkride or something you'd like to ask a DPE, I'll be on that Facebook group able to answer those questions. And then if you join the group later on, you'll be able to go back through the kind of the group content and see other questions that have been brought up. So I think that's going to be value added, and I'm kind of excited to go on that. Anyway, let's get started with our multi-engine topic. So I've got my airman certifications, my custom kind of interactive ACS. So it makes it easy to kind of navigate through the multi-engine add-on. So the multi-engine add-on section, we went through the additional task table on and how to use that last week. Or on last episode. So on this episode, we're going to jump straight to Area of Operation 9. In Area of Operation 9, we have 3 tasks that we have to complete. The first one is Task E, and that's engine failure during takeoff before VMC. So there are only 2 skills associated with this. So I'm going to read off those 2, per my normal routine here. We're going to read off each skill and then go into detail about the whole task here. So skill 1 is close the throttles smoothly and promptly when a simulated engine failure occurs. Skill 2, maintain directional control and apply brakes or flight controls as necessary. And it's brakes for multi-engine land and flight controls for multi-engine C. So the reason that that's different is in a multi-engine seaplane, you do not have brakes. On any seaplane, you don't have brakes. So you can't apply brakes. You have to apply flight controls to control the aircraft and do that appropriately. So for multi-engine land, you're going to have to add brakes to abort the takeoff. So this is all about having an engine failure prior to you rotating and aborting the takeoff. There is a major safety item here, and it's actually in Appendix 7 and Appendix 6. But Appendix 7 here are emergency operations for Task E. It says the engine failure simulated during takeoff should be accomplished prior to reaching 50% of the calculated VMC. So that right there tells me that either you or the examiner, or both of you, really should brief the fact that any simulated engine failure during the takeoff roll will occur at no more than 50% of the calculated VMC. So I'll just use the travel air, for instance. About 84 miles an hour is our calculated VMC. So half of that, we'll just round down and call it 40 miles an hour. So I would expect any engine failures, and as an examiner, I would present any engine failures on the runway prior to reaching 40 miles an hour. After we reach 40 miles an hour, we need to put ourselves in this protected zone where we're not going to simulate any engine failures, because any high-speed engine failure could result in an actual emergency, right? So if I simulate an engine failure at 80, there's a good chance that if you react improperly as an applicant, or if you're doing this in a training environment, you react improperly as a student, that you could actually crash the airplane. So we want to protect ourselves there. So that's kind of a safety practice that we do, and this is going to be a low-speed reject. Now, the training environment, I mean, from the training standpoint, it would be better if we could fail the engine right at rotate. It's way too dangerous to do that. So when you get to the airlines, actually, a Level D simulator, which is a real high fidelity, hyper realistic airplane, it looks identical to the actual airframe, right? It's way more complex even than like a real nice Redbird sim, which you've probably seen before. But this thing looks exactly like the aircraft. The flight profiles or the motion of the sim is going to be hyper realistic. So you're going to do these engine failures in the sim, and it's going to feel real, But even in the airline world, you're not going to do these in the actual aircraft. It'd just be way too dangerous. So that's just one of the trade-offs that exists in all training. We want the training to be as realistic as possible, but we also don't want to hurt ourselves when we're training. So that's why we have this option in here. Now, engine failure before takeoff, this is a real-world scenario. I've got real-world experience here where I've actually lost an engine on takeoff. So just real quick, let me tell you the story. I was flying a turbocharged Baron, a B-58 TC, and we were in Colorado at a high-density altitude, and I had 3 passengers on board. This is during the summertime, and the density altitude was around 8,000 feet. During the run-up, I never went full power because in a turbocharged aircraft, you really don't need to go full power in the run-up. It's not called for in the checklist. Now, if I'd have been in a normally aspirated airplane, it is a good idea, especially in high-density altitudes, to go to full power and lean the mixture until you get peak performance and then take off with that mixture setting. Well, I wasn't doing that because I was in a turbocharged airplane. So when I roll out on the runway and go full power, immediately I get a big directional control problem towards the left engine or towards the left side of the runway, and I have difficulty maintaining runway centerline, and I just abort the takeoff because it's way more than just the regular left turning tendencies that you get in a high performance twin. It was a lot of drag. At first, I thought my non-pilot passenger had inadvertently stepped on the rudder. That's my first instinct, and I remember thinking that why is this guy standing on the rudder? But as I cleared the runway, I kind of glanced over, and his feet were nowhere near the rudder pedals. So I tell Tower that I need to taxi back to the run-up area. They cancel my takeoff clearance. I go back to the run-up area, and now I go up to full power and realize that the left engine is only making 20 inches of manifold pressure, while the right engine is making about 39, which is what it should be. So that immediately demonstrated to me that the turbocharger had some sort of failure on the left engine, and that what I was experiencing during the takeoff roll was actually asymmetric power. It didn't have anything to do with a rudder or a blown tire, which those are the two things that first came to mind. So it felt like somebody standing on the rudder. So ever since then, when I'm presenting this during a Checkride, I typically I add rudder either left or right during the early stages of the takeoff roll. I don't do anything with the throttles. Now, that is a technique. I've seen MEIs and examiners reach up and maybe pull a mixture back or pull a throttle back as you're taking off to simulate the engine failure. That's fine. I choose not to present the failure that way because if, let's say, I pull the mixture on the left engine and the applicant makes the wrong control inputs, it's going to take some time for me to react, either pull the other mixture back or put the mixture back that I just pulled back. It's going to take me a while to manipulate the controls to correct the asymmetric thrust problem. And in that time, we could put the plane off the side of the runway. And in fact, I've seen probably once a year, we see a multi-engine aircraft go off the side of the runway. And I'm pretty sure that those are mostly due to, I would say, some poor technique from an MEI that's trying to simulate an engine failure on takeoff. I've found that simulating it with the rudder, first of all, is very realistic because I've had this happen before in real life, and that's what it felt like was rudder problem. It's also much easier to correct an improper control input if you're just doing it with rudder. So you're a lot less likely to have an actual emergency by simulating it with the rudder. Of course, this is just my technique as an examiner. Other examiners may pull the throttle, they may pull the mixture. I guess they could pull the prop. Some of those are options. Me personally, I like doing the simulated failure with the rudder. It's just me. Okay, next we have area of operation 9 task F, and that's engine failure after liftoff simulated. So This has 10 skills, a little bit more here. And so skill 1, promptly recognize an engine failure, maintain control, utilize appropriate emergency procedures. Skill 2, establish VYSE. If obstructions are present, establish VXSE or VMC plus 5 knots, whichever is greater, until obstructions are cleared. Then transition to VYSE. Skill 3, reduce drag by retracting landing gear and flaps in accordance with the manufacturer's guidance. Skill 4, simulate feathering the propeller on the inoperative engine. Evaluator should then establish zero thrust on the inoperative engine. Skill 5, use flight controls in proper combination as recommended by the manufacturer or as required to maintain best performance and trim as required. Skill 6, monitor the operating engine and make adjustments as necessary. Skill 7, recognize the airplane's performance capabilities. If a climb is not possible at VYSE, maintain VYSE and return to the departure airport for landing or initiate an approach to the most suitable landing area available. Skill 8, simulate securing the inoperative engine. Skill 9, maintain heading plus or minus 10 degrees, airspeed plus or minus 5 knots. Skill 10, complete the appropriate checklist. So, big picture, this is your engine failure immediately after takeoff. Now, there is a actual requirement here in Appendix 6. So if you go back to Appendix 6, if you remember back from a few episodes ago, Appendix 6 is where we talk about safety of flight concerns. And on this, it says the evaluator must not simulate failure of an engine until attaining at least VYSE at an altitude no lower than 400 feet AGL. So what this means is I'm going to simulate failing your engine after takeoff, but I'm going to wait until we're 400 feet above the ground. So here at Russellville, we have a field elevation of around 400 feet. So I wait until I see 800 feet on the clock altimeter, and at 800 feet, then I simulate the engine failure. I do this by pulling the throttle back. So below 3,500 feet, and I do this in all my briefings for multi-engine, below 3,500 feet, I'm not actually shutting down an engine on purpose. For simulated purposes, right? So I will not completely fail an engine below 3,500 feet. I'll just simulate it. And when I simulate below 3,500 feet, I'm only going to do that using the throttle. I'm not going to pull mixture. I'm not going to feather the prop. I'm not going to turn the fuel off. I do this because of safety concerns. Because below 3,500 feet, you don't have a lot of time to fix any problems. So, for instance, if you turn the fuel selector off to simulate failing an engine, well, that engine's actually going to fail, right? It's going to start producing zero thrust, a lot of drag, and no fuel's going to the engine. Well, if I turn the fuel selector back on and maybe I've developed vapor lock or some other issues and I'm at a low altitude, well, I might just have caused an actual emergency. So while trying to simulate an emergency, I've caused an actual one. And that's something that we want to avoid, especially during a check ride, but really all times when we're doing any type of training. We want to do it as safe as possible. So I'm only going to simulate using the throttle, first of all. I'm going to wait until I'm 400 feet because anything below 400 feet, that's low altitude, and that could easily turn into an actual emergency. So a low altitude engine failure, not going to happen. Well, it should not happen in your multi-engine training or during your multi-engine check ride. So if you have a CFI that's pulling your engine below 400 feet, you really need to point out this restriction to them in the ACS and kind of have a discussion on, is that the best way to manage risk during multi-engine training? Now, I've heard this before, and it's actually, you've probably heard the term V1 cut, or if you haven't, look it up. V1 cut, something you're going to do in all your ATP level training or type rating rides in a big turbine or turboprop or turbojet, turbofan. You're going to practice a V1 cut. And V1 cut means you lose your engine at rotate. Well, we don't do that in your primary multi-training in a light piston twin. First of all, we don't have a V1. We don't have a published V1. We can talk about that later. Probably in the next episode, we'll get into kind of those sorts of details. But we don't have a published V1 in the Travel Air or the Baron or the Seminole or the Duchess or the Technam, whatever you're using as a light twin doesn't have a published V1. So we're just not doing that. And second of all, if we had a published V1, we would only do that V1 cut in a simulator because that's the only safe place to do it. Again, read back to our previous conversation about failing the engine on the ground. We're not going to do that at a real high airspeed because of safety. So first and foremost, we're going to simulate at or above 400 feet. The second thing is notice how there's no mention in the skill set about analyzing the type of failure. It just wants you to identify the correct failed engine and immediately feather it. Okay, so we're not going to try to solve or fix the problem that is wrong with our engine. Unlike the next maneuver, the next maneuver will actually, or some of the later multi-engine maneuvers, will actually talk about analyzing why the engine failed and trying to fix it before we feather it. The reason is if my propeller's out there windmilling, so spinning around, my engine's spinning. If my engine's spinning, my mags are going, my fuel pump's going, my oil pump's going. Everything is operating, right? There's just not combustion happening for whatever reason. And combustion could not happen there's kind of three, the triangle of combustion, right? It's either spark, fuel, or air. My engine has lost either spark, fuel, or air, or the combination of those three. And if I can reintroduce spark, fuel, or air, my engine's going to start working again. So the most common reason for an engine failure is fuel starvation or fuel exhaustion. Those are the two most common reasons for an engine failure in general aviation. So most of the time, my fuel pump quit. I ran out of fuel. The tank that I have selected doesn't have any fuel in it. I'm having some sort of fuel delivery issue, like maybe an injector, the injection system has failed somehow. Maybe I've vapor locked, right? So there's vaporized fuel in the line and it's getting compressed and it's not sending that liquid fuel to be combusted properly. So I'm losing power that way. That's the most common reason. Other reasons, it could be an ignition problem, right? Maybe I've lost a magneto or both magnetos. A catastrophic failure of the main gear box in the back of the engine, the accessory gear drive. One of those gears could have failed, and that would cause both of my magnetos to fail potentially. So there's lots of reasons, but the most common one is fuel. At low altitudes, we're not even worried about that. All we're worried about is maintaining directional control and staying above blue line. Those are the two primary concerns. If you maintain heading and you maintain blue line, you will not crash your twin. You just won't. You'll maintain control. Now, you may not be able to climb, right? Because we're dealing with light twins here, and that's defined as any twin engine aircraft that weighs less than 6,000 pounds. So if you're less than 6,000 pounds, the manufacturer is not required to ensure that you have single engine climb performance. That's not a requirement. So there's a lot of airplanes that don't have single engine climb performance that weigh less than 6,000 pounds. That may initially sound like, wow, that sounds really dangerous. But remember, your previous aircraft you've been flying to this point only have one engine. So when that engine fails, well, they definitely don't have climb performance, right? You're forced to land all the time in like a 172 or a Cherokee. If you lose your engine, well, you don't have any other options at all. So flying a light twin isn't any more dangerous than flying a single engine piston. You have to think about it a little different. The most dangerous thing I think in the twin is believing you have performance when you don't. That can be really dangerous. The same kind of thing could be said about a single engine aircraft. When you lose the engine, trying to extend the glide, right? We've probably read these stories or accident investigations where somebody loses an engine. They were able to glide almost to the airport, but right like 3 miles prior to the airport, they stall spin. And it turns out they were getting low to the ground. They got a little ground shy. Instead of holding that best glide, they pulled back and they got slow and they stalled the airplane and they spun, right? That's if they would have just done a forced landing in a field and not tried to extend their glide, they would have been fine. Well, a lot of the same thing holds true for the twin, where if you lose an engine, if you just say, okay, I'm going to close both throttles and land straight ahead, yeah, that's not ideal. You're going to crash, right? You're going to do a forced landing off the runway. That's a crash. But you're going to do it under control, and you're going to do it at a slow airspeed or at a landing speed, right? And main thing is it's under control. If you try to continue flying on one engine and you don't have that performance, you're going to hit the ground in a bank with one engine at full power, one engine windmilling or feathered, and at not a slow airspeed, right? You're going to be at blue line, which might be 20 or 30 knots above kind of your full stall landing condition. So you're going to be going much faster, have much more energy to dissipate. You're not going to be wings level, and you're going to have one engine at full power. That's a terrible way to do a forced landing. So in this condition at low altitudes, hey, if you can fly away, that's great. If not, you're going to land straight ahead. There's no plain kind of maintenance investigation and trying to figure out why your engine failed. You just want to get that engine feathered, get that drag out of there, so you can hopefully establish a positive climb away from the ground and either return to the field or land straight ahead. Now, what in the travel air here in Arkansas, what we train is below 400 feet. If you lose an engine, you're going to land straight ahead, no matter what. So if you lose an engine below 400 feet, pull both throttles back to idle, choose a landing spot. Hopefully there's a runway in front of you, but if not, no big deal. You're going to choose the best forced landing area, 20 degrees left or right of the nose. No ifs, ands, or buts. That's the decision that we've made. At ground speed 0, below 400 feet, we're not going to try to fly away. That might sound a little weird, but a little bit of the decision-making behind that is at 400 feet, it's probably going to take you 5 to 10 seconds conservatively to figure out that you've even had an engine failure, right? You're not just going to react immediately. It's going to take some time. So in that 10 seconds, you're still moving across the ground. You've got an engine windmilling now. So with an engine windmilling, you've started to lose altitude, right? There's no way that your single engine there's no way that with one engine in a travel air, one engine operating at full power, the other one windmilling, you're going to be able to climb at all. You just can't. You're going to be coming down. So as soon as the engine failure happens, you have 10 seconds of descending. Then it's going to take you another 10 to 15 seconds to do your control, configure, identify, verify, feather, all your flow, get that engine secured, feather it. Now you've got the engine feathered. It's been 30 seconds since the engine failure accident or incident has occurred, right? You've lost maybe 100 or 200 feet even, and now you're starting a climb away at maybe 100 or 200 feet a minute. So 2 minutes from the time you lost your engine, 2 minutes later, you've now traveled across the ground about 1.5 miles a minute. So you're pretty far away from the runway now, and you're still at 400 feet AGL. That's a really low altitude. So now you're swerving to avoid obstacles. You may be getting ground shy. You're going to get slow, and you're going to spin potentially, right? The other option is okay, I'm just going to close both throttles. I have full control of the plane now, and I'm going to land straight ahead. So that's what this maneuver is testing here. Now, since we're above 400 feet, we're going to try to fly away, and we're going to do that by control, configure, identify, verify, feather. That's kind of the flow we're going through. We're going to control our heading and airspeed. We're going to configure the aircraft with gear up, flaps up, and everything full forward, right? So our props, our throttles, and our mixture full forward. So that's control, configure, identify the dead engine. We're going to do that by the dead foot or dead engine or dead foot dead engine mantra. So if we're holding the heading, you're going to hold heading using a lot of, if in case of a left engine failure here, we have the left engine failed, the plane's going to want to yaw to the left pretty hard. So you're going to have to add a bunch of right rudder. Your left foot won't be doing anything. So it's going to be dead. So dead foot. So then we have a hypothesis. Hey, I think my left engine is dead. You're going to verify that by selecting the left throttle, and you're going to pull the left throttle slowly but firmly back to idle. Now, you get the left throttle all the way back to idle. If things didn't get worse, then you just verified. So that was your verification step. So identified, dead foot, dead engine, verify with throttle, and then feather is the last step. And you're going to take the feather lever, pull it all the way back. That's going to feather the propeller, line it up with the wind stream, and the propeller and the engine are actually going to stop moving completely. So that's what's going to happen once you feather the engine. Now, remember, we're doing this at a low altitude. So in a training environment and a Checkride environment, all this is going to be simulated. All that's going to happen is I'm going to reach up as the examiner, I'm going to grab the left throttle and move it back to idle, and I'm going to say simulated. And that's just a safe word for me to let you know that what just happened was a simulated event. It wasn't an actual failure. At that point, you're going to go through your control, configure, identify, verify, feather. When you get to the feather step, I'm going to have you select the feather handle and start to pull it back, because I want you to develop that muscle memory, right? I don't want you to just point at it. I want you to commit to a handle, start to pull it back. I'm going to block the prop lever movement with my hand and say my propeller. When you feel me do that, you're going to let go of the propeller lever, and then I'm going to move the throttle up to about 12 inches of manifold pressure, which simulates a feathered propeller. So that's like a zero thrust setting, and that's where you hear in the ACS it says the evaluator should then establish zero thrust on the inoperative engine. So that's what it's talking about, is I'm moving the throttle up to about 12 inches, so just above idle, and it's making basically enough thrust to offset the drag. So that's a zero thrust setting. Now, down here, we're going to continue just with another detail here of maintain heading plus or minus 10 degrees and airspeed plus or minus 5 knots. So that's the most difficult thing about this maneuver is if you have a heading bug on your plane, use it during this maneuver. You want to hold heading plus or minus 10 degrees. It's easy to exceed that with all this asymmetric thrust that's going to happen. So the plane's going to want to yaw severely into the dead engine. So you need to be on your toes and ready to add as much rudder as necessary to control that heading. You want to control heading, control airspeed. Control heading, control airspeed. Those are the two most important things. Now, controlling airspeed might require you to lower the nose quite a bit because we're losing like 80% of our performance. Even though we're losing half of our power, we're losing over half of our performance. So while blue line might have been, pulling the nose up around the horizon, might have been blue line with both engines operating. With one engine operating, you might have to lower that nose maybe a few inches below the horizon to maintain that blue line airspeed. So maintain heading, maintain airspeed. If you do both of those things, you're going to be good to go. All right, our next one is Area of Operation 9, Task G, and it is approach and landing with an inoperative engine simulated for airplane multi-engine land and sea. There are 10 skills here. I'm going to read through these real quickly. Skill 1, promptly recognize an engine failure and maintain positive aircraft control. Skill 2, set the engine controls, reduce drag, identify and verify the inoperative engine, and simulate feathering the propeller on the inoperative engine. Evaluator should then establish zero thrust on the inoperative engine. Use flight controls in the proper combination as recommended by the manufacturer or as required to maintain best performance and trim as required. Skill 4, follow the manufacturer's recommended emergency procedures. Skill 5, monitor the operating engine and make adjustments as necessary. Skill 6, maintain the manufacturer's recommended approach airspeed plus or minus 5 knots in the landing configuration with a stabilized approach until landing is assured. Skill 7, make smooth, timely, and correct control application before, during, and after round out and touchdown. Skill 8, touchdown on the first 1/3 of the available runway landing surface with no drift, with the airplane's longitudinal axis aligned with and over the runway center line or landing path. Skill 9, maintain directional control and appropriate crosswind correction throughout the approach and landing. And Skill 10, complete the appropriate checklist. All right, so this is our approach and landing with an inoperative engine. This is normally an instrument approach. So it's not necessarily an instrument approach because we could do this with let's say we have a basic commercial pilot that doesn't have an instrument rating, so he's got a restricted commercial, and they're adding a multi-engine rating onto that, so they're not doing the instrument approach. This could be done with just an approach to landing, so like some sort of visual approach or pattern. This could apply to that, or in the majority of the time, so I'd say 9 times, 99% of the time even, this is going to be an instrument approach. So what we're doing is we're simulating an engine failure. You're going through the control, configure, identify, verify, feather, and you're flying that approach using only one engine all the way down to the landing. So we have to take this all the way from the approach all the way to landing. So this is a landing event, our approach and landing with one engine inoperative. So that is Task G. That's the last one of Area of Operation 9. Now we're into Area of Operation 10. This is multi-engine operations. So we have to do everything in Area of Operation 10. And we're going to start with Task A, which is maneuvering with one engine inoperative. So maneuvering with one engine inoperative, there are 8 skills here. Skill 1, recognize an engine failure, maintain control, use manufacturer's memory item procedures, and utilize appropriate emergency procedures. Skill 2, set the engine controls, identify and verify the inoperative engine and feather the appropriate propeller. Skill 3, use the flight controls in proper combination as recommended by the manufacturer or as required to maintain best performance and trim as required. Skill 4, attempt to determine and resolve the reason for the engine failure. Skill 5, secure the inoperative engine and monitor the operating engine to make necessary adjustments. Skill 6, restart the inoperative engine using the manufacturer's restart procedures. Skill 7, maintain altitude plus or minus 100 feet or a minimum sink rate if applicable, airspeed plus or minus 10 knots, and selected heading plus or minus 10 degrees. Skill 8, complete the appropriate checklist. Are you nervous about an upcoming check ride? Have you ever wondered what it's like to be a designated pilot examiner? In this show, I give you a behind-the-scenes look of the FAA check ride process. I'll show you best practices on how to have a successful check ride, common errors that applicants struggle with, and share with you some of the valuable knowledge I've gained throughout my 15-year career in military and civilian aviation. For more information about the show, visit our website, vsl.aero/podcast. There you'll find the show library, various ways to support the show, and links to purchase our interactive Airman Certification Standards Study Guide. Don't forget to like, subscribe, and leave a 5-star review. And most importantly, tell your aviation friends about the show. This is listener-supported content, and I'm planning on keeping it that way. So any way you can support the show through Patreon or PayPal is greatly appreciated. Consider how much you would normally pay for an hour of ground school with an experienced CFI. Thanks for listening, and back to the show. So, maneuvering with one engine inoperative is a little different, right? We're going to do this in conjunction with another another task of our engine shutdown. So we're going to shut down the engine. We're going to feather it. Then we're going to run a checklist to figure out, okay, why did that engine fail? We're going to check our fuel, our mags, our alternate air, our carb heat, whatever the checklist says. We're going to pull out the appropriate checklist and try to determine why that engine failed. What this turns into in the check ride is it's kind of a short discussion that we have in flight of the applicant sitting there telling me what they're going to troubleshoot, and me as the examiners, I'm just checking the box. Yes, you covered all the things in the checklist. I'll probably say, okay, none of those worked. What do we do now? And you're like, well, I'm going to continue to feather the engine. I'm going to secure that engine, and I'm going to return to the field and land. And I'll say, okay, very good. That task is complete. Let's go ahead and now run the restart checklist. So the plane you're flying should have some sort of air start checklist. If the manufacturer doesn't have one, your flight school needs to have developed one. But in all of my experience, the Light Twins have some sort of air start procedure for this reason, right? So we're going to go through that air start procedure, and we're going to restart the engine. Now, during this time, we want to maintain plus or minus 100 feet or minimum sink rate. That's a very important or, because there is an altitude requirement here unless the plane's just physically incapable of maintaining altitude. And we run into that here in Arkansas in the travel air. It's a lower powered twin. We get up to 6,000 or 7,000 feet where this is required to do at, because you don't want to actually shut down an engine at low altitude, right? Just in case something bad happens, you want to have a lot of altitude to be able to make it easily back to the airport and land safely, just in case you can't get the engine restarted. So we're not going out and doing this below 3,000 feet. In fact, we're doing it usually above 5,000 feet. So you're going to be up at altitude. Well, at 5,000 feet on a hot summer day, my density altitude might be 10,000 feet or 8,000 feet. So the plane might not be able to, once I get it shut down, the plane might actually start this drift down scenario here. So the ACS actually allows for that. It says plus or minus 100 feet or minimum sink rate. So the main thing is when you're doing all this, maintain your heading, maintain blue line, and you get what you get. If you maintain altitude, great. If not, you're doing your best to minimize the sink rate, and that's the best that I can ask as an examiner. So that's kind of an interesting thing to point out there. The other thing is, hey, this is feathering the engine and then restarting it. We're actually going to feather it. So that's something important to remember. Next one, Area of Operation 10, Task B. This is our VMC demonstration. This is a fun one. So there are 8 skills here. Skill 1's kind of exploded out into 7 different subgroups, so I'll go through that real quick. Skill 1, configure the airplane in accordance with the manufacturer's recommendations. In the absence of the manufacturer's recommendation, then at VYSE as appropriate, and the landing gear retracted, flaps set for takeoff, cowl flaps set for takeoff, trim set for takeoff, propellers set for high RPM, power on the critical engine is reduced to idle, and the propeller is windmilling. and power on the operating engine is set to take off for maximum available power. So those are 7 things that they're kind of like the combat's acronym. We'll go through that. Oh, well, I guess this is a good time to go through it now. That's your worst case scenario, essentially, is your critical engine's windmilling. You have full power on the operative engine. Your gear and flaps are up. You're outside of ground effect. That's the most asymmetric thrust you can experience. Now, because we're doing the VMC maneuver up at a high altitude, this isn't really the worst case scenario because our density altitude is actually pretty low up there. In fact, in chapter 13, I'm going to scroll over and show you, there's a chart here that shows how VMC decreases as you increase altitude. So I'm scrolling over and I'll give you a page number here. It's page 13-27 in the Airplane Flying Handbook. And you can see here that as your density altitude increases, your VMC, which is the red line on this chart, decreases. And it kind of swaps over where your loss of directional control happens after stall. So you're actually going to stall the wing before you lose control. Well, that could be super dangerous because in this scenario, right, we're raising the dead, we're splitting the ball, we have full power on our operative engine, and our failed engine is windmilling. The only way in this configuration we can decrease speed is to pull the nose up. So as we pull the nose up, the plane wants to bank further into that dead engine, requiring us to add more right aileron. Well, that drops this aileron over here. That raises the aileron over here. And now we're in the scenario where this wing is trying to do a power on stall, and this wing's trying to do a power off stall. That's kind of a good way to think about it. And if you actually go out and test this, you'll notice that in any single engine airplane, the power on stall will happen at a much lower airspeed than the power off stall. So the power off wing is going to stall at a higher airspeed than the power on wing, which means the wings are not going to stall symmetrically. And when that happens, we call that a spin. And so that's what we're tracking to during a VMC maneuver, a VMC demonstration. You're getting really close to stalling the dead engine wing. And if that does occur, what you're going to see is a rapid roll to the left. In fact, there's a great YouTube video you can look up. In fact, you can see here as the plane, I'm going to pause it right there, you can see that that aileron position is deflected down. So this is a king air, it's dropping jumpers. There's a whole scenario based behind this, but this is the perfect example of what a VMC or what a stall looks like when you're doing a VMC maneuver. So long story short, this king air is basically doing the VMC maneuver unintentionally. He's got the left engine pulled back because that's the side that the jumpers are coming out of. The jumper, he doesn't want to blast his jumpers with the prop blast. So the left engine's back at idle. Critical engine's windmilling. The operative engine is at takeoff power, and he's pulling the nose up. You can see the nose increase right before the roll happens. So the nose comes up, the airspeed drops, and then all of a sudden that left wing just stalls, and that's where you see him go into this aggressive spin, and he just rolls right over inverted. Now, this is something that kind of honestly, it irritates me a little bit because I hear a lot of people, when they see a twin crash, they're very quick to call it a VMC roll. And that kind of grates me a little bit because it's not a VMC roll, it's just a spin, right? Planes roll inverted rapidly because of spins, right? Well, especially twins. Not because of VMC. Now, VMC is the path that led them to that spin. So in an accident investigation term, I might call the VMC or the asymmetric thrust a contributing factor, but it's not causal, right? The thing that caused the plane to roll inverted was a spin. That was the causal factor. A contributing factor to that was the pilot's reaction to the asymmetric thrust. So asymmetric thrust didn't roll the plane inverted. The pilot's reaction to the asymmetric thrust is what rolled them inverted. So why does this matter? Well, when we're doing our VMC demonstration, if we're not really careful as MEIs and me as an examiner, if I'm not really careful, what could happen is I could put us in a situation where we're in an actual spin up at altitude, And once you get in a spin and a twin, the engines, now, I've got fuel out here. I've got fuel in the wings, and then I've got these two big engines, a couple 100 pounds each. Well, 300 or 400 pounds with all the accessories. And they start acting like big flyweights. So when the plane enters a spin, now these engines are acting like, kids on a merry-go-round when they move outside. You start getting pulled further and further to the edge of the merry-go-round. And as you spin, this is going to enter kind of it's going to be more of an inertial spin than an aerodynamic spin, and you're not going to have enough flight controls to recover from it, and you're going to be losing altitude very rapidly, and there's a good chance you won't recover. So we've lost our fair share of twins in doing this maneuver. So it's a dangerous maneuver. I'm not going to sugarcoat it at all. You want to make sure your MEI understands very clearly how to do this safely, and that you're doing it at a safe altitude, and putting some protections in place to make sure that you don't stall the airplane first. And so it hints to this in here. In the VMC demonstration, it says, recognize indications of loss of directional control, stall warning, or buffet. So you want to recover at the first sign of loss of directional control or buffet or stall warning. So if a stall light or horn comes on, recover. If you feel a buffet, recover. If you feel a loss of directional control, recover. As an MEI, there's a couple of things you can do to make this happen earlier. A common technique that's actually talked about in Chapter 13 is blocking rudder movement. So the ACS actually tells you to reach full rudder deflection, right? And I believe it says that in Skill 4, right? So the ACS is saying reach full rudder deflection. Well, I could also block and simulate rudder deflection, is limited, and then you're going to lose directional control earlier, which means you're going to have a margin over stall where that happens. So that's a good way to simulate. The American Bonanza Society trains Baron pilots in a way that's not in conjunction with the FAA. It says to lock the ailerons neutral, and that increases VMC significantly, right? There's verbiage in Chapter 13 about holding the wings level, makes VMC significantly higher. In fact, we can see in Chapter 13 again, I'm going to scroll over to where it's talking about VMC in different configurations. And right here on, let me see, page 13-28, it talks about with the wings level, VMC is significantly higher than published, and there is no horizontal component of lift available to help the rudder and combat asymmetric thrust. So what that means is VMC is going to happen well before, the VMC loss of control is going to happen well before your stall speed because you've artificially increased VMC. Normally that's a bad thing, but in training, we want it to happen before stall speed. So this is a technique that we use in the American Bonanza Society to help this maneuver happen at a safer airspeed and not potentially spin the airplane while we're trying to do one of these maneuvers. So that's something to think about. The next one is our our Area of Operation 10, Task C, one engine inoperative, simulated, solely by reference to instruments during straight and level flight turns. So this is just flying the airplane with one engine inoperative, straight and level and in turns. There are 11 skills here. Skill 1, promptly recognize an engine failure, maintain positive airplane control. Skill 2, set the engine controls, reduce drag, identify and verify the inoperative engine, then simulate feathering the propeller and inoperative engine. Evaluator should then establish zero thrust on the inoperative engine. Establish a best engine inoperative speed and trim the airplane. So that's skill 3. Skill 4, use flight controls in the proper combination as recommended by the manufacturer or is required to maintain best performance and trim as required. Skill 5, verify the prescribed checklist procedures normally used for securing the inoperative engine. Skill 6, attempt to determine and resolve the reason for the engine failure. Skill 7, monitor engine functions and make necessary adjustments. Skill 8, maintain the specific altitude plus or minus 100 feet or minimum sink rate if applicable, airspeed plus or minus 10 knots, and specified heading plus or minus 10 degrees. Skill 9, assess the airplane's performance capability and decide an appropriate action to ensure safe landing. Skill 10, avoid loss of airplane control or attempted flight contrary to the engine inoperative operating limitations of the airplane. Skill 11, utilize SRM. So right here is just, I've failed the engine on you and you're under the hood. So there's a certain part of this Checkride which is done with the foggles on, which is contradictory to your single engine commercial Checkride, right? If you remember back on our discussion of the single engine commercial Checkride, we don't use the foggles at all during that Checkride. During the multi-engine add-on for commercial, we do use the foggles, and this is one of those times where I'm going to have you put the foggles on. I'm going to have you handle an engine failure, and then we're going to leave the foggles on, and you're actually going to fly in and do a single engine instrument approach under the foggles. So that leads us into task D, which is instrument approach and landing with an inoperative engine simulated solely by reference to instruments. There are 13 skills here. Skill 1, promptly recognize engine failure and maintain positive airplane control. Skill 2, set the engine controls, reduce drag, verify the inoperative engine, and simulate feathering the propeller on the inoperative engine. I'll establish zero thrust then. Skill 3, use flight controls in the proper combination as recommended by the manufacturer or is required to maintain best performance and trim as required. Skill 4, follow the manufacturer's recommended emergency procedures. Skill 5, monitor the operating engine and make necessary adjustments. Skill 6, request and follow an actual or simulated ATC clearance for an instrument approach. Skill 7, maintain altitude plus or minus 100 feet or minimum sync rate if applicable, airspeed plus or minus 10 knots and selected heading plus or minus 10 degrees. Skill 8, establish a rate of descent that will ensure arrival at the MDA or decision height with the airplane in a position from which a descent to landing on the intended runway can be made, either straight in or circle as appropriate. Skill 9, on final approach segment, maintain vertical and lateral guidance within 3/4 scale deflection. Skill 10, avoid loss of airplane control or attempted flight contrary to the operating limitations of the airplane. Skill 11, comply with the published criteria for the aircraft approach category if circling. Skill 12, execute a normal landing. Skill 13, complete the appropriate checklist. All right, so that's our instrument approach. Some things to point out. 3/4 scale deflection. So you want to be able to control the airplane to get 3/4 scale deflection both in the vertical and lateral guidance. As a rule, I always present this simulated single engine instrument approach as a precision approach, either on an LPV or an ILS. I want to give you vertical guidance and I want to give you lateral guidance. The main reason I'm doing that is in the real world, I would expect you to fly a precision approach in actual weather conditions with an inoperative engine, right? Things have to be pretty desperate if I'm going to attempt a non-precision circling approach with an engine inoperative, right? Things have to be really bad for me to try to do that. To me, that's not like a realistic scenario, and it's also extremely challenging. Now, maybe I'm wrong there. Maybe I should be evaluating the hardest thing possible. But to me, that's bad risk management, right? If I lose my engine, one of the reasons I'm flying a twin is it gives me options, right? I'm up at 6,000 feet. I lose my engine. I'm able to maintain 6,000 feet. Well, I'm going to use my cross-feed system to extend my range if necessary so I can fly somewhere where I have pretty high ceilings and don't have to even worry about shooting an approach down to minimums, right? I'm going to use that higher level decision-making to make sure I don't need to use my higher level skill. So during a check ride, I would rather see you use a precision approach because in the real world, that's what I would expect you to use. It's also a little more challenging to have to follow the vertical glide slope as well as the lateral CDI. So I'm going to expect you to maintain both of those on your way down the approach and then conduct a normal landing. All right, that takes us all the way through area of operation 10, 9 and 10. And then if we go back to our multi-engine operations, you can see that 10, area of operation 11, none are required. Now, if we look at area of operation 11, that's our post-flight procedures. So, I mean, yeah, those aren't required, but you are going to have to do post-flight procedures at the end of the check ride. So, the main thing here is once we're done with this profile, don't quit flying the airplane and make some boneheaded mistake as we're taxiing in. We're keeping it serious and professional all the way until we're in the chocks, engine shut down, period, full stop. So some things to discuss further. The instrument approach, so area of operation 10, task D, that's going to be concurrently logged with area of operation 9, task G. Those are the same things. So we're only doing one, approach and landing with an inoperative engine. We don't have to do two. So we're doing kind of three tasks there. We're doing a normal landing, an approach to landing with an inoperative engine, and we're also doing an instrument approach to a landing. So those three things are kind of done concurrently. The one engine inoperative straight and level flight and turns under instruments, that's going to be concurrently done with your instrument approach and landing single engine. So what I mean by this, I'm going to try to be as efficient as possible. So my normal profile is I'm going to describe a condition generally that's going to force you to shut down your own engine. It might be a fire. It might be a major oil leak. It might be severe vibration. Something, I'm going to describe a condition that the correct answer is going to be for you to shut down and secure that engine. Okay? I'm probably going to do that after I have you put the foggles on. So you're going to do that all under the foggles, holding plus or minus 10 degrees, plus or minus 10 knots, plus or minus 100 feet or minimum drift. So you're going to do all that under the hood. You're going to restart the engine. I'm going to then immediately set zero thrust. So we're going to pretend like we never restarted the engine. We actually did, but we're going to pretend like it's still dead. And then I'm going to give you a clearance to go fly to the initial approach fix and fly the instrument approach. Doing all of that is going to count for at least 4 of these tasks here. So they won't be broken up into individual engine failures. In fact, typically I brief on a given multi-engine check ride, you're going to have 4 engine failures. 1 on the ground, 1 after takeoff, 1 in cruise, and 1 on the approach. Those are your 4 engine failures that are going to happen. And in all those cases, I'm going to say the word simulated before I give you that engine failure, because the last thing I want to do is kind of play a trick on you, like pretend, make you look out for traffic, then reach down and turn the fuel off. That's something I love to do as an MEI. And I think in the right briefing and the right training environment, that's a good thing to do. I want you to be surprised by an engine failure in training. That's something that I really want you to do. I'm not going to do that in a check ride, mainly because check rides are already stressful enough. I don't want the way that I present an emergency to you as an applicant to lead you down the path of a disapproval. And by me playing tricks, as it were, that could easily be misinterpreted. It could cause you to panic and think it's a real emergency, and things could go downhill quickly. So I just don't do that personally as a DPE. I'm very clear about that. Where I get that from is the Air Force. In the Air Force, we simulate everything and we brief. We use crew resource management to brief, hey, when we simulate something, we're going to use the word simulated. And that way, if something does happen for real and nobody said simulated, we're all going to be like, hey, I think there's an actual emergency happening now. Let's knock off this check ride and handle this actual emergency, which is exactly what could happen in a multi-engine scenario. In fact, one of these is actually talked about in area of operation, or in Appendix 6, which is our safety of flight information. It talks about several multi-engine considerations. So one of those is in Area of Operation 6 here, it says, for safety reasons, when the practical test is conducted in an airplane, the applicant must perform tasks that require feathering or shutdown only under condition at a position and altitude where it is possible to make a safe landing on an established airport if there is difficulty in unfeathering the propeller or restarting the engine. The evaluator must select an entry altitude that will allow the single-engine demonstration tasks to be completed no lower than 3,000 feet AGL or the manufacturer's recommended altitude, whichever is higher. If it is not possible to unfeather the propeller or restart the engine while airborne, the applicant and evaluator should treat the situation as an emergency. At altitudes lower than 3,000 feet AGL, engine failure should be simulated by reducing throttle to idle and establishing zero thrust. So I've been talking about that already a couple of times here. When I simulate a failure below 3,000 feet, I'm going to do that only with the throttle. Now, once we're above 3,000 or above the manufacturer's recommended altitude, again, for the Beechcraft, that's 5,000 feet AGL, I will shut down the engine, or you will shut down the engine using all the available methods. So you're going to pull the mixture, you're going to pull the throttle, feather the propeller, turn the fuel off, turn the mags off, all that stuff you're going to do for real as long as we're above 5,000. If we can't get the engine restarted, we now turn it into an emergency aircraft. Even though we did that emergency to ourselves, we're going to consider ourselves now, hey, we're an emergency aircraft. Checkride is over. We're just two people trying to get on the ground as safe as possible. That's what's going on there. I've had to do this on maybe 3 or 4 different check rides where we couldn't restart the engine. After we shut it down in flight, we couldn't restart it, and we have to land single engine. None of those have resulted in a disapproval. And they could have, right? Just because you had an emergency doesn't mean everything's erased and it's not a disapproval anymore. It just happens that all of those applicants held the plane within the ACS standards, but that item of the emergency is a true emergency, right? That's no longer a simulated emergency. That's an actual emergency, and we're going to come in and land. Now, I don't magically become PIC as the evaluator, and in fact, in all those cases that I just said, the applicant landed the airplane for real single engine. They landed the airplane single engine because, hey, that's what they were trained to do, right? And that's actually a good thing to see as an examiner. It's like, well, hey, we didn't simulate that. That was an actual single engine landing, and you did it great. Good job. Let's get the engine restarted on the ground, and we'll go up and we'll finish the rest of the test. In all cases, we were able to do that. There's, we can get into engines at a later date. If you want me to, I plan on doing kind of an engine series where we're going to go out in the shop and actually look at these engines torn down and the feather mechanisms and how this actually works. But because if you don't have an unfeathering accumulator in flight, these engines can be really hard to start in flight. And then if you combine that with an underpowered airplane, well, you're up here at 5,000 feet. You shut down the engine, and then you begin this drift down, right? Because in the summertime you can't maintain altitude, so you're drifting down, and eventually you get to 3,000 feet. We haven't restarted the engine. It's like, okay, guys, we're going to stop messing around and we're just going to land. We might be at the starter duty cycle limit, right? We don't want to burn up the starter and cause a bigger problem, so we're just going to land single engine. That's just the way it is with some of these twins. Luckily, the Travel Air has unfeathering accumulators, and that nitrogen system is able to kind of pop the blades back into a position where they begin to windmill on their own, and you don't even have to use the starter. So that's really rare that we ever have to do that in a Travel Air. Other airplanes is not so rare. I used to fly a Seneca 2, and this actually happened more than once on the Seneca 2 because that Continental TSI 0360 was really difficult to air start in certain conditions. So that might occur. And area of operation, the Appendix 6, Safety of Flight Information, specifically addresses that. All right, let me see if there's anything else to cover. I think that's about it. We've gone through the Appendix 6 remarks, the Appendix 7 for multi-engine, engine failure during flight, sole reference to instruments, and the landing with an inoperative engine by sole reference to instruments. Area of Operation 7 says 2 things here. The task is not required if an instrument-rated applicant has previously demonstrated instrument proficiency in a multi-engine airplane, or if the applicant does not hold an instrument airplane rating. And then the same thing is said for Task D. So Task C and D in Area of Operation 10 are not required if you've already demonstrated those skills in the private pilot level, or you don't hold an instrument rating. So to put it more plainly, let's say you get your private single rating, and then you get your private multi rating, and then you get your instrument rating in a multi-engine airplane. That instrument rating is going to require you do a single engine instrument approach. So then when you go get your commercial multi rating, you don't have to do the instrument work because you've already demonstrated proficiency during your instrument or your private pilot check ride. Hopefully that makes sense. So this happens every once in a while. Normally it's with owner operators, right? In fact, tomorrow I have a private pilot multi-engine check ride, and then that's from a person that owned a Bonanza. He did his private in a 172, and then he bought a Bonanza. Then he got his multi-engine private rating, right, in a twin, and he bought a Baron. Now he wants to do his instrument rating, and he's doing his instrument rating, his initial instrument, in the Baron, which is totally allowed, and I think it's a really good idea because he got all this good instrument training in the actual plane he's going to be flying day to day. Well, if he ever wants to get his multi-engine commercial rating, he won't have to do instrument procedures again on that check ride because he will have already demonstrated them during this instrument check ride. So hopefully that all makes sense. So read up on Area of Operation 7 because it might relieve you from having to do certain skills during the check ride. And of course, this is all up to the evaluator, your DPE's discretion. If your DPE says, no, I think I'm going to have you go ahead and accomplish that instrument approach, single engine, then you're going to have to do it. The evaluator's allowed to do that. It's just they don't have to because of the stuff I mentioned in Appendix 7. All right. So we've covered all the area of operations for the tasks for multi-engine. We've covered the Part 61 training. Now I think what we have left to do is talk about some of the multi-engine specific stuff. I would like to hear your feedback of me incorporating the video. So I've got the video section in this. I might delve more into that video and talk more about VMC. I would also like to have a discussion about accelerate stop and accelerate go. Those are two things I'd like to talk about, and then the full feathering propeller system. So I can think off the top of my head, maybe three more episodes on multi-engine stuff specifically. But I'd like to hear what you have to say. So please provide me feedback with anything else multi-engine related you'd like to hear in this series that we're doing on the multi-engine rating. I really appreciate you listening. I hope you'll consider financially supporting the show through Patreon. You can find out more about the show at vsl.aero/podcast. There you'll find the interactive airman certification standards that I've been using here for commercial rating. You can purchase those. And you can find out more on the Patreon page about the Facebook group, the closed Facebook group that's kind of that pilot mentorship. And there you can ask me all sorts of questions that you want if you're going towards one of these check rides and you have some questions you'd like to ask a DPE. So thanks again for watching, and I'll see you next time. See ya.